Welcome, Fride Vullum-Bruer. She's a senior research scientist from SINTEF, and she's going to talk about batteries. Thank you.
Okay, thank you for the introduction. Can you all hear me well?
Yes, we hear you, see you, and see the slides.
Great, perfect. All right. Yeah, so I'm happy to, well, first of all, thank you for the invitation, and I'm happy to be the last speaker here. It's been quite a few interesting talks before me. I know I'm going to focus mostly on the science in this talk, but I want to show a couple of slides first that really shows all the activity that's going on in Norway at the moment for batteries. And also it shows why I've chosen the topic I have. Obviously batteries, it's, you know, a variety of different types. You have primary batteries that are non-rechargeable, there's secondary batteries that are rechargeable, and there's alkaline, there's lithium batteries, there's a variety of different types. I'm going to focus today on the lithium-ion battery, and I'm going to try to explain why as well. So this map, it's a very busy map, but it shows a lot of the main activities just in Norway that's going on in the battery business right now. On the on the right-hand side, you can see a lot of the research institutes that have significant activities in batteries. On the left-hand side, there are many of the main industry players that are involved in batteries. And there you have, of course, the big initiatives with Freyr, Morrow, and Beyonder, which are planning on producing battery cells. And then there's other companies like Elkem that are now building a big plant for graphite production. And there are also other companies that are in the materials production and other areas of the battery value chain. So there's a lot of activity going on in Norway at the moment, and also in Europe as well. And I also wanted to show this. These are estimations that were made by McKinsey for a report that was launched last year by the NHO. And it shows the value creation potential for 6 main value chains in Norway. And as you can see here, this is unfortunately, it's just in Norwegian, so I apologize for that. But here is the value chain for batteries, and it's expected that it could have a turnover potential of 9 billion euros per year by 2030 and 18 billion euros by 2050. And this is just in Norway. So it has huge potential for value creation in Norway and in Europe. Right, so a little bit more introduction. This also shows a bit why lithium-ion batteries are the technology of choice. Because if you look at the figure down on the left here, you see the energy density, both in terms of volume on the y-axis and in terms of weight on the x-axis, the energy density of lithium-ion batteries compared to other technologies. And lithium-ion is superior when it comes to energy density and power density. The right-hand side, I'm not going to focus figure here. I'm not going to focus too much on now, but I'm coming back to it. So here you see on the bottom part shows the typical anode materials, and the top part in the blue ovals, these are the typical cathode chemistries. And I will come back to those later. But let's just have a look at, so batteries. These are extremely complex systems with many variables. Because they're closed systems, they're also often very difficult to characterize and analyze. But you have to have a wide variety of knowledge and background to be able to fully understand it. And obviously, I don't have time today to go through all of this. So I'm going to focus on a couple of main areas, which is also the areas where I have most of my background. And that's materials. So understanding the physics and chemistry of the materials, understanding how and why they work the way they do, looking at crystal structure, ionic connectivity, interfaces, and then be able to perform basic materials characterization. Also, hand in hand with the materials goes the electrochemistry. Be able to understand the electrochemical behavior of the materials, which also gives us information on the storage capacity, rate capability, meaning how fast you can charge and discharge a battery, lifetime, internal resistance, and so on. So I'm going to try and touch on to some of these areas throughout my talk today. Now, let's just start with how a battery works and what are the main components of the lithium-ion battery. If you look at this figure right here, on the right-hand side, you have the cathode, which comes in a powder form. Then the pink little dots here, that's the lithium. And then these are coated on an aluminium current collector. On the anode side, you have generally graphite. That's the most common material, which probably most of you have in your laptop and cell phone batteries. That is coated on a copper foil. In between here, there's a liquid electrolyte. And in order to prevent the short circuiting, so that the anode and the cathode doesn't touch, you have to have a separator. That's normally a porous polymer film that's used. And if we look at how do these actually work, so when you charge your battery, so when you plug it in to the socket and charge it, you have lithium ions going through the electrolyte from the cathode to the anode, accompanied by, of course, the electrons going in the outer circuit. This is a fully charged battery. Now, when you discharge your battery, when you use it to power your device, the opposite occurs. So lithium ion goes from the anode to the cathode, and you have the electrons to power your device. That's well, sounds very simple, but tends to be complex. Right. So some of the there are some what we call key performance indicators that we use to evaluate the battery, its suitability, and what it can be used for. These are the 6 main factors: are energy, power, cycle life, safety, cost, and environmental benignity. And this latter is also becoming more and more important as the new EU battery directive is taking shape. But I'm not going to talk about that part today. I'm going to focus on the science and mostly look at the energy and the power and what lies behind this. But then if we look at, so some of you may have heard about talk about different battery chemistries. When we say different battery chemistries in relation to lithium ion batteries, we're talking about different cathode chemistries using different cathode materials. Here we also often use a lot of short terms. So for instance, NCA, that's short for the lithium nickel cobalt aluminium oxide. NMC, or NCM, as some prefer to say, is the lithium nickel manganese cobalt oxide. Then there's the LMO, which is the lithium manganese spinel oxide. And another material which is becoming more and more relevant is the LFP material, which is the lithium iron phosphate. And if you look at these 4, and you see like none of them really fulfill all the different criteria. If you have high specific energy, you don't have the high specific power. If you go for the safety, as with LFP, you have to sacrifice some specific energy, maybe also some cost and performance. So there's, at least currently, there's no sort of perfect material. And just to note, this right here, the lithium titanate, it's an anode material, but it's an oxide and it's a bit different from the regular graphite. Lithium titanate is used in some specific applications which requires higher safety, and I will come back to that a little bit later. So if we have a look at the cathodes, so I'm going to start with that. Cathodes are currently the limiting element for higher energy density batteries. There's a limitation to how much lithium you can store in a cathode material and then take, cycle back in and out of the material. And you have sort of two important factors. You have the voltage, which is indicated by, if you look at this figure here, you see where the plateau is. But then there's also the discharge capacity, or the specific energy density, as we can say here. The specific capacity. So that's often referred to in milliampere hours per gram. But if you look at the energy density, that depends on both the capacity and the voltage. So if you have a battery with high voltage but low discharge capacity, your total energy density would be lower than if you could increase then the discharge capacity. So the energy density is essentially the integral under the curve, or you can integrate the area under the curve of the galvanostatic cycling curve. But of course, if you do a quick calculation in this curve, you will find an energy density which is over 500 watt-hours per kilogram. But if you look at practical batteries, they're nowhere near that number. But that's because if you look at a battery system, that contains also the battery management, the packaging, the cooling systems, everything, all the electronics that goes with the management of the batteries. That's also included in the total energy density of the battery, meaning that you have a much lower energy density of the total system than you would have of the separate materials. And if you look at also another factor that's important to keep in mind is that the cathode specific capacity, each material has a theoretical capacity. That doesn't mean that you're able to utilize that in a practical battery cell. The theoretical capacity is quite simple to calculate. You take the number of charge carriers, multiply by the Faraday constant, and divide by the molecular weight. So I've given an example here for the lithium cobalt oxide, where you have a theoretical capacity of about 274 milliamp hours per gram. But in practice, you get about 170, which is also shown if you look at the figure here. That's the green line here. The reason for that is that when you start taking lithium out of the structure, and you can have the structure for the lithium cobalt oxide is shown up here in A, where you see the green dots, that's the lithium ions. And these polyhedra, those are in this case, the cobalt oxide octahedra. In the case of, if you have nickel or manganese in there as well, you would have nickel or manganese occupying the middle of the octahedra. So the NMC, the lithium cobalt oxide, and also another material termed NCA, they all have the same basic structure, which is this layered structure right here. When you start taking these lithium ions out of the structure starts changing, and you get phase changes in there. If you take out more than about 55% of the lithium and the lithium cobalt oxide, the structure starts collapsing, and it goes through irreversible phase changes. And then you can no longer get the lithium back into the structure. So that's why you're not able to utilize all the theoretical capacity in a material. If you look at some of the other structures that I've shown here, and this is important, I'm going to come back to this. This up to your far right, this is a lithium manganese spinel that's shown in this red line in the figure. The lithium manganese spinel has lithium diffusion in 3 directions because it's a channeled structure. lithium iron phosphate, which is the blue line here, shown in figure C, that also has the channel structure, but it's only in, it's like a one dimensional, it's like tubes going down. So it has a bit slower conductivity, as we're gonna look more into. Oh, and yeah, one thing I forgot to also mention here, which I wanted to say something about. You will see in some of these figures, you see, for instance, the lithium manganese oxide, or sorry, no, the lithium iron phosphate here, the blue line, that's quite flat plateau. Whereas if you look at the, for instance, this orange line, the lithium, the NMC material, it has a much more sloping structure or sloping shape. The reason for that is that you have different mechanisms for the discharge. So when you have this sloping structure, that means that you form a solid solution. The lithium forms a solid solution with its host structure. Whereas if you have a flat plateau like this, it means that you have a first order phase transition. So it's slightly different mechanisms for the insertion and deinsertion of the lithium ions. Sometimes you will also see two stages, which I'm going to go back quickly. In the blue line here, you will see two stages. In this case, it's because you have both manganese and iron, and they are reduced or oxidized at slightly different potentials. So you will see several steps in your curve. All right, let's move on to the next. The cathode material structure is extremely important to understand, to be able to understand how the lithium-ion batteries behave, and both their lifetime, their capacities, and so on. So obviously, higher conductivity of the lithium ions also gives you higher rate capability, meaning that you can charge and discharge your battery faster without losing performance. Structure can also explain instabilities, promote phase change. You can have structure deterioration. Sometimes you have amorphization, or also something that's called cation switching. The latter is something that's prominent, for instance, in the NMC materials, where the lithium tends to switch places with the nickel. And in doing so, you block lithium, further lithium diffusion in the structure. So it's very detrimental to the structure. When we characterize these materials, X-ray diffraction is one of our most important characterization tools. And the main theory behind this is Bragg's law. So for those of you that teach students, teach them Bragg's law. That's one of the really important things to understand if you want to understand materials and structures. Here we obviously X-ray diffraction, it's only used for crystalline structures, crystalline materials. If you have an amorphous material, you're not going to be able to see anything because it depends on an X-ray wave coming in and diffracting from the structure as shown in here. The data that you get out looks something like this, where you have a diffractogram showing clear diffraction lines, and the diffraction lines indicate then the planes in the structure. If you have this particular figure shows the nickel, cobalt, aluminium with this specific composition, 80% nickel, 15% cobalt, and 5% aluminium. If you change up this ratio, these diffraction lines will remain, but you will start to see diffraction lines moving either to your right or to your left. So if you have a higher 2 theta value, so this big line moving down to your left, that means you're increasing the inner layer distance in your structure. And when you take lithium out of the structure, you will see often a decrease. So you can see also, we were able also to do in situ and operando characterizations, meaning that we can run X-ray diffraction as we are charging and discharging a cell. These are more complex operations and not very easy to do, but it gives us very valuable information about what happens in the material as we cycle. Also, just very briefly about the basic principles of diffusion. So if you have self-diffusion, which ideally doesn't happen in lithium-ion batteries, because then you would have self-discharge. But in the case of lithium-ion batteries, you would have ionic conduction, where you have an electric field, which is then a gradient in chemical potential, pushing the lithium ions through the structure. Here is the basic equation for connectivity, and the N here is just number of charge carriers, and the Q is to charge, and then you have mu, which is the mobility of the ion. The mobility will depend on the activation energy for diffusion. In many cathode materials, this one is relatively high, meaning it's around 0.4 to 0.6 electron volts. Also, the available diffusion channels, which I've shown in these different structures. You also have some extrinsic and intrinsic defects in materials, which will also affect the conductivity, and of course the temperature. However, temperature in lithium-ion batteries are generally, at least ideally, they should be operated at about 20 to 25 degrees, because higher and lower temperatures will have a great effect on the liquid electrolyte. Now, also very quickly before I go to the anodes, so why is fast charging challenging? That's something that often comes up in many discussions, and obviously also a great challenge for EVs or other applications. Now, in this case, this is an example where you have NMC 811, meaning that you have 80% nickel, 10% manganese, 10% cobalt, and you have a graphite anode. These are charged at various rates and then discharged at what's termed C/5, meaning that it's discharged within 5 hours. So 1C means it's fully charged or discharged within 1 hour. What we see here in the top figure is that you have, when you increase the charge rate, you have great polarization, and you see a drastic decrease in the capacity. So the overpotential is just growing. That means that you're not able to utilize all the available capacity when you increase the C rate. And in this case, which I also included here, so this is what we call a full cell with the cathode and a graphite. Here, they've done just what's termed a half cell, meaning that you cycle the cathode material against a lithium metal. That shows that you have much lower polarization, and you also have a less dramatic loss of capacity. That indicates that in this case, it's the graphite that's the limiting electrode for the rate when you fast charge. Not in the capacity sense, but for how fast you can charge and discharge your cell. So here just shows that because you have limiting ionic conductivity, you are also limiting the speed, how fast you can charge your battery. Another factor which you can't really see from these figures, but which is also important to think about for anyone that has an EV and wonder why you shouldn't be fast charging all the time. Fast charging can cause lithium plating on your anode. If you do that continuously, you will eventually form dendrites, which will short circuit your battery, and that's not good. Anyway, let's move over to the anode side, which is also a very important part of the battery, obviously. On the anode, most common material to use is, as mentioned, graphite. One of the challenges on the anode side is that the electrochemical potential is beyond the stability window of the electrolyte. So if you see here, you have the LUMO and HOMO levels of the electrolyte are not, they are sort of below the electrochemical potential of the anode. So what happens is that when you discharge or when you actually, it's when you charge it. So when you take the lithium ions from the cathode and into the anode, you start, when you go beyond a certain potential, which is shown here, about below about 1.1 volts, you start to decompose the electrolyte. And you can see here on the black line, which is the first curve or the first cycle, and the blue line is the second cycle. So the black right here shows where this SEI, solid electrolyte interface layer, is formed. For the lithium titanate that I mentioned previously, lithium titanate, it discharges at, or charges at, a very different potential. It's at about 1.5 volts, meaning that you stay within the electrochemical stability window of the electrolyte, and you avoid this decomposition of the electrolyte, which is why it's often used in applications where safety is a big issue, because the SEI can also become unstable. It consumes lithium, and it's over time deteriorates the properties of your battery. If we look at quickly at the composition of the SEI is probably one of the most studied parts of the lithium-ion battery, because it's extremely difficult to characterize and to get a grasp of. Obviously, first of all, it also changes depending on your electrolyte composition. We know that also additives are often used to form stable SEIs, because the SEI is necessary to protect from further decomposition. So if you have a stable SEI, you have a first cycle sort of decomposition, and then you prevent further deterioration of your electrolyte, or at least almost prevent, because no matter what you do, the SEI will grow over time and keep consuming lithium. This figure shows just some of the known components of the SEI. It contains lithium fluoride, lithium carbonates, and also decomposed elements of the organic components of the electrolyte. For silicon, and this is something that I wanted to mention, because some of you might have heard about the silicon used as anodes in lithium-ion batteries. Tesla has already started to implement silicon in their graphite anodes. There's also several companies in Norway that are working on producing silicon materials for lithium-ion batteries. Silicon has a really big theoretical capacity, about 10 times that of graphite. But if you are going to utilize the capacity of silicon, you see that it expands about 300 to 400% compared to its original size. When you take the lithium back out, the material will start cracking and you form new surfaces. Each time you form a new surface, new SEIs will form. And eventually you consume all your electrolyte. And you also have the problem of breaking up your particles, and you lose contact between your particles, and you lose contact with your current collector. The SEM images, so the microscopy images to your right here, shows an electrode that's then the top one is a pristine electrode. The bottom one is an electrode that's been cycled. And this shows how the SEI just fills up the voids in your structure. This is a composite with silicon and graphite. So the SEI problem and the expansion and cracking problem of silicon is really big issues that are trying to be solved.
Sorry, Fride, we're running out of time.
Yeah, and I'm to my last slide. So, yeah, so my main takeaways, and to kind of see some future challenges, batteries are extremely complex and require knowledge within a variety of disciplines. Some of the main challenges is probably related to the electrolytes, solid state batteries, which I haven't touched on to today. but also sufficient ionic conductivity to accommodate the fast charging, and of course, increasing the overall energy density of the battery system. So that was all I had. So thank you for your attention.
Thank you very much. There is one question in the Q&A section, sorry. Chidos is asking if there is a way to prevent the phase transition of one of these cathode materials.
Well, it's a phase transition isn't necessarily bad as long as it's reversible. But if you have an irreversible phase transition, they have tried ways of sort of stabilizing structures, but you get to a point where it's like you have a house. If you start taking things away from the house, eventually it will collapse. And it's kind of the same with these structures. They will eventually collapse if you remove too much lithium.
Okay, thanks. I have another question.
Yeah.
Does it make any difference to have a powder versus a single crystalline cathode?
Yeah, and if you have a single crystalline material, you could use in a very thin film electrode, but those aren't very useful in many applications. So the powders, obviously the powders are cast on a film so that you have binders in there to keep the powder particles together. And you want the electrode to be porous so that the electrolyte can penetrate into your electrodes. Otherwise, you're not going to be able to have much power density at all.
Okay. And can you mix cathode materials?
Absolutely. Yeah, absolutely. So many of the car manufacturers, they have batteries where you have a mixture of different cathode materials. They don't have just one, but they mix several.